In one of my favorite books, Zen and the Art of Motorcycle Maintenance, the author, Robert Pirsig, explains that quality is something that most of us can recognize, but few of us can define. As researchers, we often see that an objective assessment of quality can be very difficult and quite elusive. Nonetheless, to be effective scientists, we must learn to be critical of the research we read and of the research we produce. While assessing quality is difficult, it is not impossible. My name is Jeffrey Frank. I'm a statistician and the CEO of Stat59. In this video, I will discuss 6 common statistical traps that destroy research quality. You will learn how you can spot them in others' research and how to avoid them in your own. So what are these quality traps? 6 common quality traps that I see are not specifying the hypothesis, multiple hypothesis testing that's uncompensated for, cheating, P-value hacking, using unproven assessment tools, and, in some cases, conclusions based on too small of a sample size. Number 1, not specifying the hypothesis. What is a hypothesis? First of all, let's start with that. So a hypothesis is a claim or assertion about the value of a parameter or several parameters or the form of a probability distribution. And it is fundamental to many of the ways that we do statistics. Very important, the hypotheses should be developed before looking at or analyzing the data, before you look at the data. And hypotheses should be developed in this very standard way of the null and alternative hypothesis. The null hypothesis usually is the status quo. Okay, so in this case, if we were talking about 2 different triage methods, we would say the null hypothesis is that there is no difference in triage accuracy between START and SALT triage methods. And the alternative hypothesis would be that there is a difference in triage accuracy between SALT and START. And phrasing these properly as the null and alternative hypothesis is vitally important. Not specifying the hypothesis can be a real problem, particularly because hypotheses should be specified explicitly in the paper, and usually at the end of the introduction. So for instance, in a paper that's comparing 2 triage methods, very frequently we should see at the end of the introduction a statement such as, the null hypothesis of no difference in triage accuracy between START and SALT was tested against the 2-sided alternative of significant difference. Now, just specifying a hypothesis before looking at the data is not a trivial matter. And for any of you who are interested, this is an excellent article that you can find, which is called Guidelines for Statistical Reporting in Articles for Medical Journals. And this phrase comes out of that paper. It is critical also that authors specify how and when they developed each null hypothesis in relation to their consideration of the data. Statistical theory requires that null hypotheses be fully formed before the data are examined, indeed before even the briefest view of preliminary results. Otherwise, p-values cannot be interpreted as meaningful probabilities. Now, this is something that we all need to be very, very careful about. The way that statistical theory works, you cannot look at the data, see something that you think is interesting, then develop a p-value for that. It simply does not work that way. To me, it's much like trying to bet on a roulette wheel after it's already been spun. Of course you can tell your test works. Of course you can guess the number after you've seen the results. This is vitally important, and this is a trap that I see many researchers get themselves into. Now, do all studies need a hypothesis? Well, almost always. Some purely descriptive studies will not. They will simply describe what they see. But most good studies will have a single hypothesis. And remember, if the study has any p-values or confidence intervals, then they must have a null and alternative hypothesis. In fact, if you're using any type of statistics software to develop a p-value or to calculate a confidence interval, you have, by default, specified a null and alternative hypothesis. You might not know what it is, but the software is assuming one if you don't specify it. Absolutely must be there. Now, when you're reading through some literature and you're wondering how can I evaluate the quality of a specific study, how do I spot this trap of not specifying the hypothesis? Well, once again, always look for the null hypothesis to be specified in the paper. If the null and alternative hypotheses are not specified in the paper, then you cannot meaningfully interpret the p-values. This should be in the introduction or the background, but sometimes it's found only in the methods. Now, multiple hypothesis testing and failing to correct for multiple hypothesis testing is another quality trap that many researchers fall into. This is something that I used to see a lot. And people would come to me and say, you know, I did some research, I did a bunch of t-tests, and some of them were significant. Now I'm going to write a paper about those t-tests. Now, what's wrong with this? Superficially, it seems kind of nice. But the problem is that if you do enough tests, then for sure you will get some positive just by chance. So for instance, here is the table for the gelato experiment. And the gelato experiment is an experiment I do when I'm teaching statistics, which involves looking at an additive to ice cream and seeing if it increases ice cream consumption. And here we can see a table. And here we have a table where there's 20 p-values. Okay, so the tests are rejected or not rejected in 20 different rows of this table. And this is classic bad use of statistics. So if you are doing this, multiple hypothesis testing, you're doing 20 hypotheses, then we need to have this noted in the paper, and how you deal with this statistically must be very specific. So there are a number of tests that involve multiple comparisons inherently. So this can be things like chi-square tests and linear regression and ANOVA. And these are tests that are designed to look at that kind of testing. There's also ways of correcting for multiple comparisons. And there's a number: the Tukey-Kramer method, the Sheffey method, the Dunnett's test, Duncan's new range test, and then my favorite, the Sioux method. All of these are ways of mathematically correcting for that multiple hypothesis testing. It is not good statistical practice to simply have a long table of p-values without any compensation for the multiplicity of them. So how do you spot this trap? Well, when you're reading through research, look for long tables of p-values or multiple p-values written in the paper. And if you see those, check the methods to see if some sort of correction for the use of multiple statistical tests was used. If not, then this is a big quality trap. P-value hacking. P-value hacking is another quality trap that many researchers fall into. And this has a number of other names: data dredging, data snooping, harking or hypothesizing after the results are known, or jarking, justifying after the results are known. And this is a wonderful article called Fooling Ourselves, and I urge all of you to pick this up and read through it. It's a fantastic article explaining the hazards of p-value hacking and other mistakes that statisticians make. What's the problem with p-value hacking? Well, the author of this article, Regina Nuzzo, she says that the problem is that post hoc stories can be concocted to justify anything and everything, and so truly end up explaining nothing. Now, the important thing to remember is that p-values and confidence intervals should be used to address the initial research hypothesis only. And hypotheses developed after the viewing of the data should be clearly indicated as post hoc. Now, this is something we all like to do, and it has a very fancy name, exploratory data analysis. This is when you do your study and afterwards you find something interesting. For instance, maybe we were doing this study of start versus salt triage, and we assessed our null hypothesis and our alternative hypothesis and developed our statistical test. But afterwards, we looked and we found that we, for instance, had 3 different sites where we had done this test, and some sites were clearly different from the others. This is something we viewed post hoc, and we can do exploratory data analysis. We could plot it, we could explain it in our discussion, but we should not be using p-values on that. We do not do statistical tests on post hoc data. We can use this for hypothesis generation, and we might, in our discussion of our paper, talk about why this is important and what further studies might be used to assess it. So how do you spot this trap, the trap of p-value hacking? Well, one of the things is watch for p-values in the paper that are not part of the original hypothesis. Again, we talked that the original hypothesis should have been specified in the paper, and p-values that are not part of that hypothesis should probably not be in the paper. Watch for conclusions that appear suddenly in the discussion without being found in the results. So this is sometimes what people do. Again, with the start and salt example, the triage example, we found there was a difference between sites and one hospital was larger than the other. Maybe we'd like to mention in our discussion about that, but we must be very, very careful about making any types of significant statistical conclusions. Watch for strange justification phrases. The difference was clinically but not statistically significant. As a statistician, we know that that is completely absurd. If a result is not statistically significant, that means it was quite possibly due to chance, so it cannot be clinically significant. The difference would likely have been significant if the sample size was larger. This is absolute speculation. This is not true. In fact, statistics are there to compensate for this type of sample size. So this conclusion is absolutely not true. And such things as not absolutely significant, but nearly so. We have to be very careful of these phrases. And then really watch for strange conclusions. So, and conclusions such as male patients between 37 and 45 years of age were more likely to have sustained fatal wounds from the blast injury. It seems pretty unlikely that someone, before looking at the data, would have chosen ages 37 to 45. This sort of seems like one of those things that someone might have devised after looking at the data. And if that's in the paper, it should be clearly labeled as such. Now, p-value hacking is a very interesting thing. When I first started in statistics, the ability to make multiple p-values, to do multiple statistical tests was really hard. We were hacking these things together using software such as writing it in BASIC or trying to use Lotus or Excel to make the calculations. Now, the unfortunate problem is that it's extremely easy to calculate p-values. We can do it in seconds. And many researchers who are not experienced with the theory behind statistics will make multiple p-value tests on their data and report only those that are interesting. And this is p-value hacking, and we absolutely cannot do it. Cheating. It kind of goes without saying that cheating is something that we shouldn't be doing. But cheating can take on a number of different ways that sometimes we don't even think about. Sometimes it's data fabrication. We don't really know what happened in a specific instance of a test, so we just make something up. Excluding data that don't seem to fit. Sometimes we just get some test scores from people who were in our experimental group and they don't seem right, so we just take them out. Reporting only positive findings is another form of cheating. And then, of course, the big one, which is just out and out lying. Now, this is an extremely, extremely important part of research and a part of the ethics of science. And here where I live in Canada, we had a few years ago a very bad outcome with a child who had meningitis. And one of the things that came out in the legal hearing was this quote. He heard so many stories from parents about vaccination causing autism in their children that he and his wife decided they wouldn't vaccinate their own kids. Now, this is a very, very interesting issue because the association with autism and vaccination, I think most of us as scientists believe that is not true. However, the myth of this relation actually came from medical science, from a paper that was published, was peer-reviewed, and was accepted as good research. It was only later that we found out that the author was indeed cheating. And this shows the profound, profound effect that cheating on your research, whether it's big or small, does have implications for patient care. And cheating on your research can be harmful to the population of patients that we are trying to protect. So cheating, it happens. And how do we spot it? Well, this can be very, very difficult to identify. One of the things is to really watch for the face validity. Does this study seem to fit with other information in the literature? Because if it doesn't, then we should be very careful about making big conclusions. We should watch very carefully for unusual methods, ways things were done that we are not used to seeing, or very, very wary about unspecified methods. If you see a paper that claims to be randomized but does not explain to you in the methods how the subjects were randomized, doesn't explain where the data came from, doesn't explain who owns the data. All of these things can make us very suspicious that cheating may have gone on. And of course, it goes without saying, in your own research, we as scientists, our responsibility is to the truth, and so our responsibility is not cheating. It's producing high quality research. Number 5 on the list of quality traps is the use of unproven assessment tools. This is a very interesting problem because many of us who are working in innovative fields, I'm going to say disaster medicine, cybersecurity, we often rely on assessment tools. So these can be surveys, questionnaires, testing tools such as multiple choice tests or simulations. And these tools can be biased and can very much threaten the validity of our conclusions. Now, how do we spot this problem with unproven assessment tools? We should be very, very wary of use of assessment tools to make sure that they're validated and that they're reliable. So the first thing is to look to see if the assessment tool has been previously published and used in other studies. We should be very wary of researchers who use their own evaluation tool for the evaluation of their own innovation. Okay? One of the things we see often in medical education is the introduction of a new training technique. Perhaps we're introducing the use of simulation into an emergency medicine training curriculum. We'd like to evaluate whether the use of this new simulation technology increases the knowledge of the students about emergency medicine. If we write our own multiple choice test and give it before and after the course, our ability to bias that test and basically determine the outcome of the study is very, very important. So we should look to see that the authors have assessed the validity and the reliability of the tool in the methods. If they have not, then we have to understand that there is a huge bias in their methods. And finally, just a quick note about small sample size. which can be a quality trap, but need not be. One of the things about sample size is that small sample sizes can really be a fact of life. Now, small sample sizes do limit the generalizability of the study findings. We also know that small samples increase the chance of a type 2 error. That is, the chance that the treatment that we chose is actually effective, but we're unable to prove it. And this seems just inherently part of science. We can understand that small sample sizes will lead us to this increased risk of missing an important finding. When you're using a small sample size, then usually we should be using simple statistical techniques. Small sample size, simple statistical techniques. They go together. Authors should limit the strength of their conclusions based on small sample sizes. One of the important things to remember that small positive studies are actually positive. And that's what the p-value is all about. So if we say we have a p-value of 0.01 in a large study, or we have a p-value of 0.01 in a small study, what we're saying is that our probability that we committed a type 1 error, the probability that we determined the study as positive, but it actually isn't, is actually the same. So the p-value, its design is to compensate for that. So small positive studies are positive and should be interpreted as this. Remember that small sample sizes are a fact of life for those of us who work in innovative areas of research, and that small studies often serve as an important gateway to further research. So in this video, we saw 6 statistical traps that researchers fall into, all of which can destroy the quality of research results. And those are not specifying the hypothesis, using uncorrected multiple hypothesis testing, p-value hacking, cheating, using unproven assessment tools, and failing to account for a small sample size. We learned how to spot these traps in others' research, and equally important, we learned how to recognize them in our own research. My name is Jeffrey Franck. I'm a statistician and the CEO of Stat59. To see how Stat59's AI-guided statistics software can effortlessly increase the quality of your research, please visit our website at www.stat59.com.